if I asked you, what was the loudest sound ever recorded? Chances are you'd think of a volcano.
Yeah, that seems likely.
And you'd be right. But do you really know the full story behind that sound? The one that, burst eardrums 40 miles away?
And sent pressure waves around the globe multiple times? It's
Yeah.
pretty mind-blowing stuff.
It really is. Okay,
Yeah.
Let's unpack this. We're about to embark on a deep dive into one of history's most iconic natural disasters, the 1883 eruption of Krakatoa.
Mm.
And this isn't just a story about, fire and brimstone. It's about how things escalated, the geology behind it, the immense human tragedy,
That
obviously.
global environmental fallout, which was huge.
Exactly. And also how it basically changed science. So we'll dig into the old accounts, the geology, the modern science to see why Krakatoa, why it still matters so much.
What's fascinating here is how something that seems on the surface like straightforward destruction actually holds all these interconnected lessons.
Mm.
Well, from how we perceive risk or fail to all the way to, planetary science, and even how we should be monitoring volcanoes right now, it's much more layered than just one massive bang.
It really is. And that complexity, it starts right at the beginning with how creepily the eruption built up. It wasn't just bam, out of nowhere.
No, definitely not.
The first signs were back in May 1883, May 20th. It had been dormant for ages, right? Like 2 centuries.
Yeah, over 200 years.
Then suddenly tremors, explosions, this ash and steam cloud shooting up like 6 miles high.
Audible, 100 miles away in Batavia, modern Jakarta. So not subtle exactly.
Well, subtle, no. But here's the really unsettling part. This sort of thing went on intermittently for 2 whole months.
Right, a phased escalation.
And instead of people getting worried, it apparently led to festive excitement. Can you believe that? People organized picnics nearby.
It sounds unbelievable from our perspective, doesn't it?
Totally. This normalization of risk, thinking, it's just putting on a show, that was such a critical and, tragic failure.
This raises an important question.
Mm.
How often do we mistake early warning signs for, just a spectacle, leading to this critical failure in risk perception?
Yeah.
In Krakatoa's case, that 2-month warm-up period, instead of clearing people out, it actually drew them closer. It's a really powerful example of that dangerous human tendency to just adapt, right, until it's way too late.
And for so many, it definitely was too late because the main event, the real crescendo, hit on August 26th and 27th, 1883.
Mm-hmm.
So on the 26th, the explosion started throwing debris 15 miles high. Then a black ash cloud hit 17 miles, explosions every 10 minutes, just escalating like crazy.
The intensity was ramping up fast.
Then August 27th, 4 enormous blasts, just colossal.
Right.
And the third one at 10:02 in the morning. That was it. The loudest sound in recorded history.
The one everyone talks about.
Heard 3,000 miles away on Rodrigues Island in the Indian Ocean and 2,200 miles off in Perth, Australia. People there thought it was cannon fire.
Just astonishing distances.
And the power. It ruptured the eardrums of sailors on a ship, the RMS Norham Castle, that was 40 miles away.
40 miles. Wow.
Ash from that blast shot 50 miles up into the stratosphere. And the pressure waves, they literally went around the Earth multiple times.
Recorded on barographs, instruments
Yeah.
in Britain, the U.S.
Yeah, it was the first time we really had instrumental proof of a truly global event like this.
A benchmark moment.
And in the immediate aftermath, 70% of the island, the whole archipelago, just gone, collapsed into a caldera.
Plunging the whole area into darkness for days.
2.5 days of darkness. And it threw out nearly 5 cubic miles of rock and ash. So here's where it gets really interesting. With all that power flying around, why was that specific explosion, the 10:02 a.m. one, so incredibly loud?
That's the key scientific question, isn't it? And the answer, it lies in the geology.
Yeah.
Krakatoa is in the Sunda Strait in Indonesia.
Right.
It's a classic subduction zone. You've got the Indo-Australian plate diving under the Eurasian plate.
Okay, so that friction, that movement.
Exactly. It creates these explosive stratovolcanoes like Krakatoa. And crucially, Krakatoa's magma is felsic, which means it's thick, sticky, viscous.
Like honey, almost.
Sort of, yeah. And it's rich in silicon and sulfur. So gases get trapped inside, building up enormous pressure before they blow. That's the recipe for big explosions.
Okay, so we've got the explosive potential, but what was the trigger for that specific ear-splitting blast? What are the theories?
Well, there are two main ideas, and they probably work together. The first one, and this seems most likely for the sound, is what we call a hydrovolcanic or phreatomagmatic explosion.
Frito what now?
Phreatomagmatic. Basically, think of a huge amount of seawater suddenly getting into the superheated magma chamber.
Oh, wow. Okay.
That water flashes instantly to steam, creates this massive, explosive steam cushion, like a giant natural pressure cooker bomb going off.
Right. Got it. And the second theory?
The second is that the island itself collapsed into the emptying magma chamber below a caldera collapse. And that collapse might be what allowed the seawater to rush in so fast and so violently.
So they're kind of linked, potentially.
They're very likely linked, yeah. And this brings us back to that paradox you mentioned, the sound versus the actual explosive force.
Yeah, because it was louder than Tambora, but Tambora was actually a bigger eruption, force-wise.
Exactly. Krakatoa was maybe 200 megatons of TNT equivalent.
Mm-hmm.
Tambora, back in 1815, was more like 800 megatons. Huge difference.
So why the discrepancy in sound?
Think of it like this. Tambora was maybe like a massive rocket engine firing mostly straight up, throwing out a huge amount of material.
Okay.
Krakatoa, especially that 10.02 blast, was more like the rocket itself blowing up spectacularly on the launch pad.
Ah, okay. Makes sense.
The key for the sound was that incredibly rapid, violent conversion of seawater to superheated steam inside that confined space. It created a much sharper, more intense pressure wave, acoustically speaking.
Right.
So if we connect this to the bigger picture, it tells us that sheer explosive power doesn't always equal the loudest noise. That specific interaction of water and magma can create these, well, truly disproportionate sound effects.
That distinction really helps. But while the sound went global, the human cost, that was terribly local and immediate. Over 36,000 people died.
A staggering number.
And here's something really crucial. The main killer wasn't the blast or the ash or the pyroclastic flows directly.
No, it was the tsunamis.
Exactly, generated by the volcano's collapse. Over 34,000 deaths were from the waves. Only about 4,500 from the pyroclastic flows, relatively speaking.
That's a critical point. The secondary hazard was far deadlier.
Can you even imagine waves that big? The largest was estimated at 120, maybe 135 feet high.
Unfathomable.
It wiped out 165 coastal villages on Java and Sumatra. Just gone. And get this, a steamship, the Baru, was carried almost a mile inland on Sumatra. Killed everyone aboard.
Just picked up and dumped inland. The power is incredible.
The first-hand accounts are terrifying. There was a Javanese field worker, Ahmed, about 8 kilometers inland. He saw this great black thing coming towards him.
Which was the water.
Yeah, he realized it was water. Described people desperately scrambling up slopes, many just washed away. It's chilling.
And the scale of that human tragedy was undoubtedly made much worse by the limitations of the time.
How so?
Well, in the 19th century, they just didn't have sophisticated seismographs, no real-time communication networks like we have, no way to warn people about the tsunamis.
So the waves hit with absolutely no warning.
None at all. Coastal communities were completely unaware. This raises an important question. How much of that tragedy was purely the force of nature, unavoidable, and how much was, well, a direct result of the technology and preparedness or lack thereof of the era?
A difficult question.
It's tragically a mix, but the lack of warning definitely pushed that death toll way higher than it might have been otherwise.
And the impact didn't stop at the coasts there. Krakatoa really did affect the entire planet. That sulfur dioxide, the SO2 gas,
propelled 50 miles up into the stratosphere.
Yeah. It formed these tiny sulfate aerosols, like a fine dust. And these particles, they spread around the whole globe within weeks.
Carried by the high-altitude winds. And they stayed up there for what, 1 to 3 years?
That's right. 1 to 3 years. And this atmospheric veil, it created some absolutely stunning visual effects around the world.
The famous Krakatoa sunsets.
Exactly. For almost 3 years, people everywhere saw these spectacular sunsets and sunrises. Descriptions talk about unearthly shades of chartreuse and crimson.
Almost alien colors.
Yeah. It even caused blue moons because of how the light was filtered. And many people think the swirling red sky in Edvard Munch's painting, The Scream,
was inspired by those skies.
Yeah.
That was a theory put forward by the geologist Rozier Verbeek, who studied the eruption extensively.
Amazing.
But beyond just the pretty colors, the environmental impact was serious. That aerosol layer in the stratosphere acted like a giant sunshade.
Reflecting sunlight back into space.
Exactly. It increased the Earth's albedo, its reflectivity. And that led to a noticeable cooling effect, a volcanic winter.
How much cooling are we talking?
Average global temperatures dropped by about 0.5 degree Celsius, maybe a bit more, 0.5 to 0.6 degrees C. in the year after the eruption.
Wow, that's significant.
It is. And temperatures didn't really get back to normal until about 1888, 5 years later.
5 years.
And Krakatoa's climate impact was actually a huge moment for climate science. It was really the first time that the idea of volcanic aerosols causing global cooling was widely studied and properly formulated.
So it spurred scientific understanding.
Massively. And what's fascinating here is how that single event back in the 19th century still echoes in modern climate science. There's research suggesting the cooling effect penetrated deep into the oceans.
Really?
Yeah, and lasted for decades, even temporarily slowing down some 20th century sea level rise and ocean warming. It really connects these past disasters to the climate issues we're facing right now.
That long-term ripple effect is incredible. And just to really get a handle on Krakatoa's scale, it helps to compare it to other big eruptions, right?
Absolutely. Context is key.
Like compared to Tambora in 1815, also in Indonesia, Tambora was much bigger, wasn't it?
Oh, yes. Tambora was a VEI 7 on the Volcanic Explosivity Index. Krakatoa was a VEI 6. And remember, that scale is logarithmic.
So VEI 7 is roughly 10 times bigger than VEI 6.
Roughly, yeah. In terms of ejected material, Tambora threw out about 6 times more stuff than Krakatoa, and its climate impact was much more severe.
That was the year without a summer, 1816.
Exactly. Caused widespread famine, maybe 92,000 deaths from starvation and disease, far more than Krakatoa's direct tsunami toll.
So again, we hit that paradox. Tambora was way more powerful overall, ejected more stuff, cooled the planet more, but Krakatoa had the louder bang.
Right. It comes back to that mechanism. Tambora, the huge rocket engine firing up.
Yeah.
Krakatoa, the rocket blowing up due to that water interaction, the phreatomagmatic blast.
Okay. What about, say, Vesuvius in 79 AD?
Well, both were explosive stratovolcanoes. Both erupted violently in August. Both killed thousands. But the type of destruction was different. Vesuvius buried Pompeii and Herculaneum under ash and pyroclastic flows.
Preserving them weirdly.
Right. Whereas Krakatoa's tsunamis mostly just washed everything away. And even something more recent, like Mount St. Helens in 1980.
That was a big one in our lifetimes.
It was. But it was a VEI 5, significantly less powerful than Krakatoa's VEI 6.
So Krakatoa really was in a different league in many ways.
If we connect this to the bigger picture, it really shows that raw explosive power, the VEI number, isn't the only thing that matters for impact.
Right.
The specific location, the type of magma, how it erupts, especially that water interaction for Krakatoa, can lead to vastly different but equally devastating outcomes. Krakatoa's unique place is sealed by that mechanism, the sound, and those global effects.
But the Krakatoa story, it didn't end in 1883. It's still going, isn't it, with Anak Krakatau?
A child of Krakatoa, yeah. It started growing from the caldera left by the 1883 eruption back in 1927.
Popping up and sinking again at first.
Yeah, a few times, but it permanently broke the surface in August 1930. And for decades, it just kept growing, maybe 20, 30 feet per year on average.
Building itself up with frequent smaller eruptions, a constant reminder.
A very active, very visible reminder.
Until December 22nd, 2018, when Anak Krakatau showed its own destructive side.
Tragically, yes. A major flank collapse, part of the volcano's side, slid into the sea.
Triggering another deadly tsunami.
Right. Killed over 400 people, injured thousands on the coasts of Java and Sumatra. Just devastating. And the collapse itself dramatically shrunk the volcano.
How much did it lose?
It went from about 338 meters high, over 1,100 feet, down to just 110 meters, around 360 feet. A massive chunk, just gone.
Wow.
And the research after that event revealed something really crucial, with big implications.
What was that?
Scientists figured out the collapse wasn't actually triggered by a big explosive eruption beforehand.
No. So what caused it?
It seems it was a result of longer-term sort of destabilizing processes within the volcano. The flank was getting weaker over time. The eruption we saw actually happened after the landslide started.
Like releasing pressure?
Exactly. Like a champagne cork popping off after the pressure builds. That's the analogy they used.
Okay. And why is that so significant?
Because our traditional volcano monitoring often relies heavily on tracking seismic activity, earthquakes caused by magma moving up, getting ready to erupt.
Right.
But if the biggest danger, in this case a flank collapse tsunami, can happen without that clear precursory seismic signal, just due to slow weakening, well, our standard methods might not give enough warning.
So we need other ways to watch for this kind of thing.
We definitely need to enhance monitoring with non-seismic methods like high-resolution satellite radar to detect subtle ground deformation, maybe changes in the slope stability. And tragically, back in 2018, Indonesia lacked a specific warning system tailored for tsunamis generated by volcanoes as opposed to earthquakes.
Another gap in preparedness.
It really raises an important question. If the threat comes from a silent, slow destabilization leading to a collapse, rather than a noisy, explosive buildup, how do we need to adapt our monitoring strategies, especially for volcanoes near coastlines?
Yeah, absolutely. So Anak Krakatau is now this, critical living laboratory for figuring that out.
Precisely. It's forcing volcanologists to constantly refine their approach.
And actually, the original 1883 eruption itself, it kind of did the same thing for science back then, didn't it? It was a turning point.
Huge turning point. It really helped push volcanology from being mostly descriptive, relying on anecdotes.
Like sailors' logs and local stories.
Yeah, exactly. Towards becoming a more modern predictive science. Back then, analysis was mostly after the fact. They used barometers to track the pressure waves, which was innovative for the time.
Didn't the Royal Society try to collect accounts?
They did, a sort of early crowdsourcing effort, asking for authenticated facts from observers worldwide. And that Dutch geologist, Roger Verbeek, his massive 550-page report in 1885.
That's seen as the start of modern volcanology.
Pretty much, yeah.
Sure.
But even then, seismology was just getting started. The first recording of an earthquake wave from a distant quake, a telesism, wasn't until 1889, after Krakatoa.
Wow, so contrast that with today.
Oh, it's night and day. Now we have real-time seismic networks, listening constantly for tiny earthquakes, harmonic tremors indicating magma movement.
GPS satellites.
Absolutely. Geodesy using continuous GPS and satellite radar. INSAR to measure ground deformation down to fractions of an inch. Satellites like Landsat, Aster, MODIS giving thermal images, tracking gas plumes.
Measuring the gases themselves, too.
Yeah, SO2, CO2, often with instruments on the ground or aircraft sending data continuously. It's this whole global network of monitoring.
Which Krakatoa itself kind of highlighted the need for because its effects were global.
Exactly. That global reach spurred the need for worldwide data sharing. And this modern system, it works. It allowed successful short-term forecasts, like from Mount Pinatubo in 1991.
Which saved thousands of lives.
Thousands. So if we connect this to the bigger picture, Krakatoa wasn't just a catastrophe, it's a catalyst. It actively pushed forward a scientific revolution that's still saving lives.
What a story. We've gone from, a local spectacle that turned deadly to a global climate event and then this huge driver for scientific progress. It really hammers home those lessons about secondary hazards like the tsunamis and just how crucial comprehensive preparedness is. The lack of warning in 1883, and even some of the challenges in 2018 with Anak Krakatau, they just underscore that need for constant vigilance and evolving science.
Absolutely. And that's why Krakatoa, through its child, Anak Krakatau, remains so relevant. It's this living laboratory, constantly reminding us of the planet's power and pushing us to adapt to new, sometimes unexpected volcanic threats.
So what does this all mean for us today? Well, that 2018 Anak Krakatau collapse, it showed us that a huge disaster can be triggered by these silent, long-term weakening processes, not just a big explosive buildup with clear signs.
Right, the champagne cork scenario.
Exactly. So what does that teach us about looking for similar silent destabilization in other critical systems, things beyond volcanoes, natural systems, maybe even man-made ones that could fail catastrophically with very little traditional warning? How do we spot that champagne cork getting ready to pop in other places we think are stable? Something to think about.